thank you for visiting my YouTube channel. I know you want to watch the video. Before I get into the content, I'm going to talk about my nonprofit, the Accelerated Training Program, a cybersecurity and digital literacy nonprofit based in Charlotte, North Carolina. We are looking to provide accessible cybersecurity education and digital literacy skills to underrepresented groups from the K through 12 space right now, but we have on our roadmap collegiate, elderly populations, etc. Pretty much anyone from an underrepresented group. We want them to get cybersecurity education and digital literacy skills to bring them into the ever increasing digital world that we live in now. If that sounds like something that you're interested in, we do have a donate button if you would like to donate monetarily. We're always accepting donations. If you would like to volunteer your time, we have a volunteer tab where we're looking for workshop volunteers. Currently, we have 1 month workshops, but we're looking to expand that in 2024. Board members, advisory board members, and a grant writer. So if you're a grant writer, if you have experience in grant writing and also winning grants, we would definitely love to have you on our team. To be considered, please complete the volunteer form here, which is a link that will navigate you to a Google form. And again, we're a cybersecurity, digital literacy nonprofit, and we would love to work with you if that is your passion as well. Thank you. Have a good day. And now the video is going to start. Hello, and welcome to another day, another video of the advent of cyber 2023. In today's video, we're going to focus on day 16, which is today. So far, so good. This is machine learning. Can't capture this machine. Oh, that's kind of cute. So let me start the machine. Okay, so let's start it in split screen. So let's read while it is loading. McGreedy has locked McSkitty out of his ELF TM HQ admin panel by changing the password. To make it harder for McSkitty to perform a hackback, McGreedy has altered the admin panel login so that it uses a CAPTCHA to prevent automated attacks. A CAPTCHA is a small test, like providing the numbers in an image, that needs to be performed to ensure that you are a human. This means McSkitty can't perform a brute force attack. Or does it? After the great success of using machine learning to detect defective toys and phishing emails, McSkitty is looking to you to help him build a custom brute force script which that will make use of machine language to solve the CAPTCHA and continue with the brute force attack. There is, however, a bit of irony in having a machine solve a challenge specifically designed to tell humans apart from computers. Yeah. Okay, so the learning objectives. Complex neural network structures. How does a neural network function using neural networks for optical character recognition, integrating neural networks into red team tooling. So the VM and split screen is what we have. So we already pressed the start machine, so let's keep going. Introduction. In today's task, we'll get our first look at how red teams can use machine language to help them attack systems. But before we can start attacking the admin portal, we'll need to expand on some of the machine language concepts taught in the previous tasks. Let's dive in. Okay, convolutional neural networks. In the previous task, we talked about neural network structures. However, most of these structures were fairly basic in nature. Today, we will cover an interesting structure called a convolutional neural network, or CNN. CNNs are incredible machine language structures that have the ability to extract features that can be used to train a neural network. In the previous task, we used the garbage in, garbage out principle to explain the importance of our inputs having good features. This ensures that the output from the neural network is accurate. But what if we could actually have the neural network select the important features itself? This is where CNN comes into play. In essence, CNNs are normal neural networks that simply have the feature extraction process as part of the network itself. This time, we're not just using math, but combining it with linear algebra. I have not seen that since undergrad. Again, we won't dive too deep into the math here to keep things simple. We can divide our CNN into three main components: feature extraction, fully connected layers, and classification. We're actually already covered the last two components in the previous tasks as a simple neural network structure. So our main focus for today will be on the feature extraction component. Okay, feature extraction. CNNs are often used to classify images. While we can use them with almost any data type, images are the simplest for explaining how a CNN works. This is the CAPTCHA that we are trying to crack. So we see it's 40531. Since we be using a CNN to crack captchas, let's use a single letter in the captcha as our image. So this is the 4. Image representation. The first question to answer is, how does the CNN actually perceive this image? The simplest way for a computer to perceive an image is as a 2D array of pixels. A pixel is the smallest area that can be measured in an image. Together, these pixels are what creates the image. A pixel's value describes the color that you are seeing. There are two popular formats for pixel values: RGB. The pixels is represented by three numbers from 0 to 255. These three numbers describe the intensity of the red, blue, and green colors of the pixel. Grayscale. The pixel is represented by a single number from 0 to 255. 0 means the pixel is fully black, and 255 means the pixel is fully white. Any value in between is a shade of gray. To represent the image as a 2D array, we start at the top left and capture the value of each pixel, working our way to the right in rows before moving down. Let's take a look at what this will look like for our CAPTCHA. So it starts at the top left, and you see it's adding pixels and breaking it up. And now it's doing little boxes, and each box, so this is a white and red. So now that we now that we have our representation of the image, let's take a look at what the CNN will do with the image. Convolution. There are two steps in the CNN feature extraction process that are performed as many times as needed. The first step is convolution. The math is about to get slightly hectic here, so take a deep breath and let's dive in. During the convolution step of the CNN's feature extraction, we want to reduce the size of the input. Images often have several thousand pixels, and while we could train a neural network to consider all of these pixels, it will be incredibly slow without really adding any additional accuracy. Therefore, we perform convolution to summarize the image. To do this, we move a kernel matrix across the entire image, calculating the summary. The kernel matrix is a smaller 2D array that tells us where in the image we are currently creating our summary. This kernel slides across the height and width of the image to create a summary image. Take a look at the animation below. So you see any values that have 0, which means white. Oh, no, it's taking the average and it's creating a new array. As you can see from the animation, we start at the top left of our image looking at a smaller 3x3 section. We then calculate the summary by multiplying each pixel with the value in the kernel. These kernel values can be set differently for different feature extractions, and we're not limited to a single run. The values of these kernels are usually randomized at the start and then updated as the network is busy training. We say that each kernel run will create a summary slice. As you can see from the animation, by sliding this kernel across the entire image, we can create a smaller summarized slice of our image. There are a couple of reasons why we want to do this. So, as mentioned before, we can create a neural network that takes each pixel as input, but this would be an incredibly large network without improved accuracy. The summary created by the convolution process still allows us to capture the image's important details without needing all the pixels. If our CNN's accuracy decreases, then we can simply make the kernel smaller to capture more details during the input phase. The term used for this process is sparse interaction, as the final neural network won't directly interact with each pixel. If you would like to learn more, we can read more here. If we calculate a feature in one location in our image, then that feature should be just as useful as a feature calculated in another location of the image. Making use of the same kernel to determine the summary slice means this condition is met. If we update the weights in one of our kernels, it will alter the summary for all pixels. This results in something called the property of equivalence to translation. Simply put, if we change the input in a specific way, the output will also get changed in that same way. If you would like to learn more, we could visit or read here. We perform this summary creation with several kernels to create several slices that are then sent to the next step for our CNN feature extraction process. Let me see if I can answer some of these questions because I've read quite a bit. Okay. What key process of training a neural network is taken care of by using a CNN? So, did we get there? Okay, let's say feature extraction. Yep. Okay. What is the name of the process used in the CNN to extract the features? Okay, so we need to learn about extracting features. Let's keep going. Okay. Pooling. Okay. Not that. So it's not um pooling. The second step performed in the CNN feature extraction process is pooling. Similar to convolution, the pooling step aims to further summarize the data using a statistical method. Let's take another look at our single slice and how a max pooling will provide a summary excuse me, of the max values. So we have a single depth slice. Max pool will be 2 by 2. So then we get with the kernel weights, we get a new summary slice. As you can see, again, for each kernel, we create a summary based on the statistical method. For max pooling, this is finding the maximum value in the pixels. We could also use a different statistical method, such as average pooling. This calculates the average values of the pixels. And that is basically it. That's how the CNN determines its own features. Depending on the network structure, this process of convolution and pooling can be repeated multiple times. In the end, we're left with the pooled values of each of our slices. These values now become the inputs for our neural networks. So let me see. I want to say convolution, and I'm not sure if I'm spelling that right. Yep. Okay, so that was right. What is the feature of the process used to reduce the features? I want to say pooling. Okay. Now, what off the shelf CNN can we use to train CAPTCHA cracking OCR models? Okay. Okay, fully connected layers. Now that we have our features, the next stage is really very similar to the basic neural network structure that we used back in the introduction to machine learning tasks. We will create a simple neural network that takes inputs, the summary slices from our last pooling layer, run them from the hidden layers, and then finally provide an output. This is called the fully connected layers portion of the CNN, as this is the part of the neural network where each node is reconnected to all the other nodes in the next layer. So, classification. Lastly, we need to talk about the classification portion of the CNN. This is the output layer from the fully connected layers portion. In the previous tasks, our neural networks only had one output to determine whether or not a toy was defective or whether or not an email was a phishing email. However, to crack CAPTCHAs, a simple binary output won't do, as we need the network to tell us what the character and later the sequence of characters is. Therefore, we will need an output node for each potential character. Our CAPTCHA example only contains numbers, not letters. So we need an output node from 0 to 9, totaling 10 output nodes. Having multiple output nodes creates a new interesting feature for our neural network. Instead of simply getting one answer now, all 26 outputs will have a decimal value between 0 and 1. We will then summarize this by taking the highest value as the answer from the network. However, nothing is stopping us from reviewing the top 5 answers. For instance, this can help us identify areas where our neural network might be having issues. For example, there could be a little confusion between the characters of M and N as they look fairly similar. Reviewing the output from the top 5 nodes will show us that this might be a problem. While while we may not be able to solve this confusion directly, we could actually use this to our advantage and increase our brute force accuracy. We can do this by simply discarding the CAPTCHA if it has an M or N and requesting another to avoid the problem entirely. Let me drink a little bit of water, excuse me. My throat is a little scratchy. Sorry. Okay. Training our CNN. Now that we've covered the basics, let's take a look at what will be required to train and use our CNN to crack the CAPTCHAs. Please note that the following steps have already been performed for you. The next steps will be to perform in the hosting the model section. However, understanding how training works is an important aspect, so please follow along and attempt the commands given. We will be making use of the attention OCR for our CNN model. The CNN structure has a lot more going on, such as LSTMs and sliding windows, but we won't dive deeper into these steps in this instance. The only thing to note is that we have a sliding window, which allows us to read one character at a time instead of having to solve the entire CAPTCHA in one go. So I'm going to say attention OCR. Attention OCR. Okay, so now we need to get the password, and then we need to log in. Okay, so let's go. Um, while we will be making use of the same steps followed to create CAPTCHA 22, which is a Python pip package that can be used to host a CAPTCHA cracking server. If you're interested in understanding how this works, you can have a read here. While you could try to run all of this software yourself, most of the machine language component runs on a very specific version of TensorFlow. Therefore, making use of the VM attached to the task is recommended. In order to crack CAPTCHAs, we will have to go through the following steps. Gather CAPTCHAs so we can create label data, label the CAPTCHAs to use in a supervised learning model, train our CAPTCHA cracking CNNs, verify and test our CAPTCHA cracking CNN, export and host the trained model so we can feed it CAPTCHAs to solve, create and execute a brute force script that will receive the CAPTCHA, pass it on to be solved, and then run the brute force attack. Steps 1 through 4 are quite taxing, so they have already been completed for you. We'll do a quick recap of what these steps involve before moving on to hosting the model and cracking some CAPTCHAs. To do this, okay, you have to start the Docker container, so let's open. We're going to say docker run dv temp data, and we're going to create, and this is going to be mounted on uh, temp. Hold on, temp directory. Okay, I wonder if it's going to be mounted. What is it? Data. Oh, okay. I have data twice, and I don't need that. Okay. Okay. So it's yes, it's mounted to temp data. I mean temp directory. So I had data twice. This will start a Docker container that has TensorFlow and AOCR already installed for you. You will need to connect to this container for the next few steps. First, you'll need to find the container's ID using the following command. PS is process. Take note of your container's ID and run the following command. Okay. Docker X IT. And this is my, hold on, if I make this bigger. So this is my container ID. Then bash. Okay. This will connect you to the container. You can now navigate to the following directory for the next couple of steps. Okay, so we're in the container now because you see now we're root. And inside our container ID. Gathering training data. In order to train our CAPTCHA cracking CNN, we first have to create a data set that can be used for training. Let's take a look at the authentication portal for HQ admin. So I'm going to open. Okay. So it going to Firefox, it automatically took us to the URL. And we see the authentication page. So username, password, here's our CAPTCHA, image, and then we got to put it in. As you can see, the authentication portal embeds a CAPTCHA image. We could get the raw image using a simple curl command from a normal terminal window. So let me open a new tab. I'm going to say curl http hqadmin.thm, and it's on port 8000. In the output, you'll see the base64 encoded version of the CAPTCHA image. We can write a script that will download this image and then prompt us to provide the answer for the CAPTCHA to store in a training data set. This has already been done for you. You can view the stored data using the following command in a Docker container. ALH raw data set. Oh. Oh, okay. It's wrong tab. It's this tab. ALH raw data set. Okay. Creating the training data set. Okay, you see this is all the images that are saved in the script. Next, we need to create the training data set in a format that AOCR can use. This requires us to create a simple text file that lists the path for each CAPTCHA and the correct answer. A script was used to create this text file and can be found under the labeling directory. You can use the following command to view the text file that was created. Okay. Okay, so this is it. the data set, the image, and then what the image value is. Okay. Once we have our text file, it has to be converted into a TensorFlow record that can be used for training. This has already been done for you, but you can use the following command to create the data set. So dataset labels training.txt and then training.tf records. As mentioned before, this has already been done for you and is stored in the labels directory. There. We have created two data sets, one for training and one for testing. As mentioned in the introduction to machine learning task on day 14, we need fresh data that our CNN has never seen before to test and verify that the model has been trained accurately, not overtrained. Remember the example that was used was if you know 1 plus 1 equals 2 and 2 plus 2 equals 4, what is 3 plus 3? So it could be that by overtraining, the neural network remembers the principle, so it will say 6. But it's not based on the neural network actually being trained. It's just the neural network being overtrained that it can guess the answer. Okay. Just as in the previous task, we'll only use the training data set to train the model and then the testing data set to test its accuracy. Training and testing the CNN. Finally, we can start training our model. This has already been done for you, but with all the preparation completed, you will be able to use this command to start the training. Okay, so if we say cd labels, AROCR, training.tf records. Training will now begin. Once the training has completed a couple of steps, stop it by pressing Control C. Let's take a look at one of the output lines from running the training. Okay. In each of these steps, the CNN is trained on all of our inputs, similar to what was discussed in the introduction to machine learning tasks. Each image is given as an input to the CNN, which would then make a prediction on the numbers that are present in the CAPTCHA. We then provide feedback to the CNN on how accurate its predictions are. This process is performed for each image in our training data set to complete one step of the training. The output from AOCR shows us how long it took to perform this round of training and provides feedback on the loss and perplexity values. Loss is the CNN's prediction error. The closer the value is to 0, the smaller our prediction error. If we were to start training from scratch, the loss value will be incredibly high for the first couple of rounds until the network is trained. Any loss value below 0.005 will show that the network has either completed its learning process or has overtrained on the dataset. So keep that in mind. Perplexity. Perplexity refers to how uncertain the CNN is in its prediction. The closer the value is to 1, the more certain the CNN is that its prediction is correct. Consider how perplexed the CNN will be seeing the image for the first time. Seeing something new will be perplexing, but as the network becomes more familiar with the images, it's almost as if you can't show it anything new. Any value below 1.005 will be considered a trained or overtrained CNN. As the CNN has already been trained for you, you can now test the CNN by running. Okay, so okay, so now we're going to test. Testing will now begin. Once a couple of steps are completed, you can stop it again using Control C. Let's take a look at 2 of the lines. Okay, I'm going to stop it. As you can see from the testing time, running a single image sample through the CNN is significantly faster than training it on the entire data set. This is one of the true advantages of neural networks. Once training has been completed, the network is usually quick to provide a prediction. As we can see from the predictions provided at the end of the lines, one of the CAPTCHA predictions was completely correct, whereas another was a prediction error, mistaking a 5 for a 6. If you compare the loss and perplexity values of the two samples, you will see that the CNN is uncertain about its answer. We can actually use this to our advantage when performing live predictions. We can create a discrepancy between CAPTCHA prediction accuracy and CAPTCHA submission accuracy simply by not submitting the CAPTCHAs that we are too uncertain of. Instead, we can request a new CAPTCHA. This enables us to change the OPSEC of our attack, as the logs won't show a significant amount of entries for incorrect CAPTCHA submissions. We could even take this a step further and save the CAPTCHA images that were incorrect on submission. We could then label these manually and retrain our CNN to further improve its accuracy. This way, we can create a super CAPTCHA cracking engine. You can read more about this process here. Hosting our CNN model. Now that we've trained our CNN, we'll need to host the CNN model to send in CAPTCHAs through our brute forcing script. For this, we will use TensorFlow serving. Once the CNN has been trained, we can export the weights of the different nodes. This allows us to recreate the trained network at any time. An export of the trained CNN has already been created for you under the OCR model directory. We'll now export that model from the Docker container using the following command. So we're going to say cd ocr and copy model temp directory. So what this command is saying, change to the OCR directory and run this command. So with this and, it will only be successful if the first command, both of these have to be successful. So we were able to cd or change directory to the OCR directory, and then we were able to copy the model from the temp directory. Once that's complete, you can exit the container terminal by typing exit and kill it using the following command: docker kill, and then paste my command ID, container ID. TensorFlow serving will run in a Docker container. This container will then expose an API that we can use to interface with the hosted model to send it a CAPTCHA for prediction. You can start the serving container using the following command. So I'm going to copy this. Paste. Okay, so it's starting. This will start a hosting of the OCR model that was exported from the AOCR training Docker container. We could connect to the model through the API hosted at this address. Now we're ready to help McSkitty regain access to the HQ admin portal. Okay, brute forcing the admin portal. We are now ready for our brute force attack. You've been provided with the custom script that we will use. You can find the custom script and password list on the desktop in the brute forcer folder. Excuse me. Let me go to the brute forcer folder. Jesus, I am not feeling well today. Okay, so here's the script. So the username is admin. We don't know the password. Our URL, website URL is the HQ admin on port 8000. Our model URL is what we just started here, localhost 8051. Because, oh, that's what I wanted to mention. So we're exposing 8501. We're exposing that port. And so we're saying the model URL is on the local host 8501 version 1 models and then predict. So that's pretty similar to what we had here. Okay, so then we're opening passwords.txt and we're reading it and we're saving it as word list. Then what we're doing is recreating the lines, and with the word list.read lines, it's putting each line on a separate line. And so what we're saying is we want to replace the carriage return or the enter with a space. Okay. What else? So currently our access granted is false because we haven't figured out the password, and our count is 0. So next what we do is, while the access granted is is false, and the count is less than the length of passwords. Then we are going to try a brute force attack of the password. So essentially, what we're going to do is we're going to load the next password, and then we're going to try to use that password to log in. So then what we do is we get the session, and then we take that session for inside the website URL, which will be the hqadmin.thm8000. From there, this beautiful soup, it looks like we're parsing. It's an HTML parser from the request. So this R is the request. So from this request, we're going to get the content and we're going to extract it using the HTML parser. Then we're going to get the image. We're going to find the image, and then we're going to the encoded image is we're going to split on a space, and we're going to take the second value. Okay, because remember, arrays start at 0, not at 1. So this is going to take the second value, not the first. Okay, so then we're building the JSON. We're going to have JSON is JavaScript object notation. So we're going to have two keys. We're going to have the signature name. And so this is the default. And then the inputs is the base 64 of the image. And then we're going to send that CAPTCHA to our model. And then we're going to pass in our JSON. And then we're going to save our prediction inside of the request of JSON. So essentially what is happening, we're passing in the model URL, which is this localhost 8501 models, and then we're passing in the model data as the data. So we're doing a post. So we're doing a post request, and for the URL, we're providing the values from the model data. So it's basically the base 64 encoding of the image. From there, we're going to get a response object back. And so the response object is saved into the prediction variable as a JSON. So a JavaScript object notation object. Okay, so then the probability is the prediction from the outputs and the probability. So this is a 2D array. So you're going to go to outputs and probability, and then that's going to give you the value of the probability. And then for the answer, you're going to go to predictions. In the prediction array, you're going to go to outputs and output, and then that's going to give you an answer. So if the probability is less than 90%, it's too low and we're not submitting the CAPTCHA. And so it's going to continue. So long as this access granted is false and the count is less than the length, this is going to keep going. Okay, otherwise we are good to go with our brute force. So now we're building our post data again with another JSON. So we're passing in the username, the password, the answer to the CAPTCHA, and then submit query. So then what we're going to do is we're going to call our website again, which is the HQ admin portal, and then we're going to pass in our JSON data. So this is going to be username, password, the CAPTCHA answer, and then we're invoking pressing the submit query button. So that's what this is. So when you press the button on the back end, this is how it looks. So we're mimicking that. Okay, so then from there, we're going to get a response. And then what we're doing is we're saving that response in response as text. Next, so if incorrect CAPTCHA values, if that's in the response, so if that's in the text, that let us know that our CAPTCHA was wrong. And then we need to try again. So if we see incorrect username or password, that means that we had an invalid credential pair and we increased the count. Finally, if none of these conditions are true, that means we found the password and we have found our username and password, and our access granted will be changed to true, which means the bigger loop here will be false, and then we're done. Okay. Let's dive into what the script is doing. So I kind of described it. So first we load the libraries that will be used. We'll mainly make use of Python's request library. Load our password list, which will be used for the brute force attacks. In a loop, we will perform our brute force attack, which consists of the following steps. Make a request to the HQ admin portal to get the cookie values and CAPTCHA image. Submit the CAPTCHA image to our hosted CNN model. Determine if the prediction accuracy of the CNN model was high enough to submit the CAPTCHA request. Remember, it needs to be above 90. If it's below 90%, it's not going. Submit a brute force request to the HQ admin portal with the username, password, and CAPTCHA attempt. Read the response from the HQ admin portal to determine what to do next. Okay, so I am going to open a new tab. I'm going to say CD desktop brute forcer. So the double ampersands allows you to run multiple Linux commands on one line. So this is what we're doing. Force.py. Okay, let's run it for a minute or two, and you will regain access to the admin portal. Okay, really not gonna guess this. Oh, that's kind of cute. Okay. Okay. So let me go here. Admin. Oh, sorry. Turned on my caps lock 2708084. And we're gonna log in. Captures can't hold me back. I know that's right. Paste. Okay, so in conclusion, in this task, we have shown how machine language can be used for red teaming purposes. We have also demonstrated how we can create custom scripts to perform tasks, such as brute forcing the authentication of a web application. All we need is a spark of creativity. While we could have taken a pre-trained model, such as the Tesseract OCR, it wouldn't have been nearly as accurate as the one we trained specifically for the task at hand. This is true for most machine language applications. While generic models will work to some degree, it's often better to train a new model for the specific task we're tackling. So, we have solved all the questions. If you enjoyed this room, make sure to check out the Red Teaming Learning module or learning path, excuse me. So, I hope you learned something in this video. I have, as I keep saying, I really haven't done machine learning or AI, so this is good to do it in digestible chunks. And I can't wait to see you for the next video. Have a good day. Bye.